Hello. Today we're going to talk about Lagrange multipliers and what they are, how we use them, what we're doing when we work with them. So we use Lagrange multipliers in order to maximize or minimize some surface that has a constraint upon it. You could think of constraints as being like a domain, right? We're only going to use certain values of x, y, or x, y, and z in order to contribute to this surface. And then when we have that sort of boundary on our domain, we could find extrema, absolute mins and maxes. And so we'll be working with general surfaces, and they'll always be of the form some f of x, y, z, and then, equals a function of x, y, and z, or just x and y. And then the constraint will always be of the form some function of x, y, and z, or just x and y, equal to a constant. And that's how you'll know that that's your constraint. So the idea here is that we're going to compare the level curves of a surface and our constraint function. And so what we've got right here is a picture below. In red is the constraint. That's our g of x, y is equal to k. So that's a constraint. Whereas in blue, we have the f of x, y. These are the level curves of our surface so that we can look at this two-dimensional image of it. And so what we want to see is where the constraint and the level curves would have a parallel gradient vector. So for example, right here where this point is, if I was to draw a gradient vector, remember a gradient vector will be normal to a curve. So that gradient vector is not only normal to the level curves, it is also normal to the constraint function. The opposite of this would be, let's say I pick some other point over maybe let's see, where do I want to go? I'm going to look at another intersection point here. Okay. So here I have a point where the constraint and a level curve are intersecting, but the gradient vector for the constraint is pointing out, and it actually runs parallel to my level curve, whereas the gradient vector for my level curve is pointing so that it is normal to the level curve, but now it's parallel to the constraint. So that's not the sort of point that we're looking for. This right here is what we would really call not interesting. Like something is going on there, but it's not a maximum or a minimum. Over here, where we have the gradient vector of each being the same or, at least parallel, maybe not the exact same. So maybe I'll draw two of them where they're different lengths. This is interesting because when this happens, there is an extrema here. Okay, it'll be a min or a max, we're not sure yet. And that's what we're going to try to find. All right, so let's see, I think that's all that I talked about in all the verbiage there. I did want to show you what this looks like in an animation. So this is a really cool animation. The link on the notes takes you here. This is on GeoGebra. And what we have here on the right is a surface. It looks like it is a paraboloid. And then you can see on the XY plane, the level curves projected down. And then the blue line or the blue curve that is going around on the paraboloid, that's the constraint function on our surface. And then the left image, what that is the projection that we're seeing the XY plane. And on the XY plane, we see our level curves in red. And then we also see the level projection of our constraint function. So let's see what happens when, before I start, there's a yellow dot on here, and the yellow dot has the normal vector or the gradient of the level curve as well as the normal vector for the constraint function starting at the same point. Okay, so you can see where the yellow dot is right now. Those two gradient vectors are not in relationship to each other. They are not parallel. Okay, so I'm going to start this and see what happens. Oh, it looks like down there along the negative y-axis, I stopped just a little bit before so we can still see it, but it looks like the gradient vectors are definitely going to be parallel to each other on the y-axis. And notice that they are different lengths. I'm not saying that they're the same thing or that they're equal, but one is a scalar multiple of the other. So I could keep going around. Notice they're not parallel anymore. And then when we get to, the x-axis, I see that once again, they are parallel to each other. And then in order for me to go back around, I have to start at the beginning here. And I can scroll, scroll, scroll. And now notice on the surface, the right image, the yellow dot, I can see where we are in space in 3D along our paraboloid on the constraint function. Okay. And then we're going to get up to the positive y-axis, and it's hard for me to get there perfectly. Well, I'm almost there. Okay, let's pretend I'm right there on the positive y-axis. Again, our gradient vectors are parallel to each other. And notice on the surface, this corresponds with a maximum. So like what we have to think about is that this constraint function is actually making it so that the values that are like outside of this curve are not part of what we're dealing with. We're dealing with the paraboloid, but just like the bottom of it, and then like right along the curve, only the xy values that contribute to that curve. Okay, and so we can continue going around, and it looks like when we get to the negative x-axis, it's again really hard to get there perfectly. I'm almost there. You can kind of see where when we get to the negative x-axis, they are going to be parallel. And on the back side of our surface, we can see, let me turn this a little bit, we can see we're at a minimum over there. Okay, so that's all I wanted to show you with this image, to kind of give you an idea of what it is we're working with, like visually, what are we doing? So notice that, so the gradient vectors, well, I can write this down here. No, we'll write it right here. So the gradient vectors of the surface, the level curves of the surface and of the constraint function are parallel, and I'm going to write in parentheses, not necessarily equal, because they may not be the same length. At extrema. Okay, so then that means that we need to find the xy values where the gradient vectors are parallel to each other. Okay, so the way we can say that mathematically is this little equation right here. This equation says the gradient of f is equal to some lambda times the gradient of g. Remember, f is our surface, right? So we're going to look at the gradient of our surface and then project it down onto the level curves. And we're going to say that it's equal to some constant. We don't know what that constant is. It could be 1. It could be negative 1. But it is a constant times the gradient of our constraint function. And the lambda that's in here, lambda is the Lagrange multiplier. Okay, and it's just a number. That's all it is. But we may or may not find that Lagrange multiplier as we work through these problems, but we will find the xy values that are giving us the extrema where the two gradients are equal up to some constant lambda. Okay, so here's the idea. We've got a series of steps that we have to take. First, we're going to calculate our gradient vectors. We're going to look at our surface, f of xy. We'll look at our constraint function, g of xy equals some constant, and we'll calculate the del operator of f, that's our gradient, and the del operator of g. Then we're going to set up the equality where the gradient of f is equal to lambda times the gradient of g, And remember that lambda is merely a constant. It indicates that parallel relationship, but the possibly not equal nature of that parallel relationship. One of the gradients could be longer than the other, and that's what that lambda is there for. Once we set those two vectors equal to each other, we're going to equate coefficients, and that's going to give us equations, right? We're going to get equations 1 and equations 2 from the first and second components if it's a function of x and y. If it was a function of x, y, and z, then we would get 3 equations from that. Okay, when it's just a function of x and y, we get 2 equations from the 2 first partials, and then we also get a third equation from the constraint. So the constraint always has to be satisfied as we solve this system of equations. Now, this system of equations will possibly be the most difficult system of equations you've ever worked with, because each problem presents new and different methods for solving these systems. And unfortunately, there is no be-all, end-all way that's going to work every single time. And so we just have to be willing to try something. We're going to look for relationships between the equations. We're going to look at, being a little tricky to see if we can make things work. We're going to have to look at several cases many times. We're going to have to do all the things. It's a lengthy process. And then once we find the solutions to the system, those are going to be our critical points. Okay, and we're going to examine those critical points. We're going to plug them into our surface and find out what the value of the surface is for those points. And that's going to tell us, like, the biggest one will be the absolute max and the smallest one will be the absolute min. That's how we're going to do it. Now, of course, this idea can be extended to higher dimensions. We will work with situations where we're looking at f of x, y, z. So then we'll have 3 systems from the gradient, 3 equations from the gradient, and then we'll have the constraint function. So it'll be a 4 equation system, nonlinear system. All right. And then in that case, the interesting part, when we're looking at f of x, y, z, remember that's a 4-dimensional thing that we have. And so we won't be thinking of the gradient of level curves. We're going to be looking at the gradient of level surfaces. But we won't actually be able to see this. So we're going to start with these 2 variables, work our way up to 3, knowing, like, kind of having an idea of what we're trying to find. All right. There are also cases where there's more than one constraint. There can be multiple constraints. And because this is an introductory course into multivariate functions, we're not going to do more than one constraint. All right. So let's start with an example. In this example, we're told, in all of these examples, we're supposed to use Lagrange multipliers to find the extreme values of the function subject to the given constraint. Okay, so I'm going to identify first what my constraint is. It's the equation that is equal to a number. This is my constraint. So we'll call it g of xy equals x squared plus y to the 4th is equal to 5. That's our constraint, okay? That means f of xy is our function. That's what we're trying to optimize. Okay, so the very first thing to do is to calculate the gradient of f is equal to lambda times the gradient of g. So I'm going to set up this equation of vectors. Very first thing is the gradient of f. Remember, the gradient is the vector whose components are the first partial derivatives of your function. So our function f of xy equals x squared y, the first partial with respect to x is 2xy. The first partial with respect to y is just x squared. And then I need to also calculate lambda times the gradient of g. So that's going to be lambda times the vector that has the first partial derivatives of g. The first partial derivative with respect to x is 2x, and with respect to y is 4x cubed. Okay, so what I have here now is that 2xy comma x squared vector is equal to lambda times 2x and 4, oh, I accidentally wrote in an x and I meant a y, so it's 4y cubed. Okay, now the second thing is to go ahead and list the system of equations. Using the gradients and the constraint. And then we're going to find the critical points. I will always use CPs for critical points. Okay, so the first component of our Lagrange multiplier equation says that 2xy is equal to 2x lambda. The second equation says that x squared is equal to 4y cubed lambda. And the third equation is my constraint, which says that x squared plus y to the fourth is equal to 5. So that's our system of nonlinear equations. It is nonlinear because we're not looking at things in the form of ax plus by equals c. Right? We've got squares, we've got cubes, we've got a fourth power. It's ugly. So I'm looking at this, and again, this isn't something that is intuitive. It is one of these things that you try something and you hope it works. I will be working through a few examples in order to start helping you to see what might help you solve these. So the first equation, I noticed that there's an x and a y and a lambda, and I also note, hold on. Sorry about that. Kids walking in. Okay, so I also noticed that maybe in the first equation I could factor and solve for x. Now what will be tempting to do is to divide the x out. Don't do it. Never, ever, ever divide out a possible solution. You could be dividing out the thing that gives you your critical points. So instead what we do is we actually solve our equations by moving everything to the other side. So I could write 2xy minus 2x lambda is equal to 0. Okay? Now if I factor this, there's a 2x in common. It leaves behind y minus lambda, and that's set equal to 0. This means that either x equals 0 or y is equal to lambda. Okay, so this section is going to bring up a lot of algebra, and you've got to be okay with it. You've got to be able to move things to one side, factor, and solve using the zero product property. Don't make up any other properties. And now what we have is two cases. So I'm going to call x equals 0, case 1, and y equals lambda will be case 2. And we're going to examine each one of these. So case 1, in case 1, we've got x is equal to 0. So if x is equal to 0, then in equation 2, we have 0 is equal to 4y cubed lambda. So all I did was plug in x equals 0 into equation 2. And if I solve that, then I have y equals 0 or lambda equals 0. Now, if x and y are both 0, then equation 3 is not satisfied because you can't have 0 squared plus 0 to the fourth equals 5. That just doesn't work. Okay, now if lambda equals 0, then we're assuming that y is not 0, right? It's just going to be any old number. But x is 0, so we're going to go into equation 3, and we'll have 0 squared plus y to the fourth is equal to 5, which means y is equal to plus and minus the fourth root of 5. Okay, so that gives me critical points of, let's see, x was 0, so we have 0 comma the positive fourth root of 5, and we have 0 comma the negative fourth root of 5. Okay, now the next thing I need to do is I need to find out what what my function value is at these points. So I'm going to look at f of 0 with the 4th root of 5. I have to remember what my function was. Going back up, my function is x squared y. So it means I'm looking at 0 squared times the 4th root of 5, which is going to give me 0. And furthermore, we're going to have the f of 0 with negative 4th root of 5 is going to give us the same thing because we have that 0 squared in there. So when I multiply out, I get 0. That takes care of case 1. I'm done with that one. The next one is case 2. And that is where y is equal to lambda. So I'm going to take that and I'm going to substitute this into equation 2. So in 2, if y is lambda, I get x squared is equal to 4 lambda to the 4th. Okay. And then I'm going to solve this, and I have x is equal to plus and minus 2 lambda squared. Okay, so I get 2 possible solutions for x, but they're in terms of lambda. So I'm going to take these values and sub into equation 3. So equation 3 has x squared, which that means 4 lambda to the 4th, plus y to the 4th, which means lambda to the 4th, is equal to 5. Well, I have 5 lambda to the 4th on the left, so I can divide out the 5 and have lambda to the 4th is equal to 1. I'm only interested in real solutions, so lambda is equal to plus or minus 1. Okay? Now, if lambda is equal to 1, this implies that x is equal to plus and minus 2 times 1, or just 2, and y is equal to 1. So I get a critical point. I get 2 critical points, actually, where x is, I dropped my plus and minus, plus or minus 2, and y is 1. And then we go to lambda is equal to negative 1. And this means x is equal to plus or minus 2 times negative 1 all squared, which still gives me plus or minus 2. But now y will be equal, well, y is equal to lambda, so y will be equal to negative 1. So my critical points from this case are going to be plus and minus 2 with negative 1. Okay, so I got 4 critical points here, and I need to go ahead and find the values of all of those. So I want to find, let's see, our equation is x squared y. So if I'm looking at f of plus or minus 2 with 1, I'm going to get plus or minus 2 all squared times 1, which is just going to give me 4. And if I look at f of plus or minus 2 with negative 1, that's going to give me plus or minus 2 all squared times negative 1, which gives me negative 4. So sometimes when the points are going to give you the identical values with the function, we just plug them in that way. I realize it's a bit unconventional. But what I'm seeing here is 3 values. I've got 0, 0, 4, and negative 4. Those were all the things that came out of using the Lagrange multiplier method. And so what do these mean? Well, the biggest one is the absolute max. So our absolute max is f of plus or minus 2 with 1. So that's 2 critical points, which gives us 4 every time. And our absolute min is f of plus or minus 2 with negative 1, and that gives us negative 4. And those are our final answers. This is all that work to put a box around a 2-line statement. That's it. Okay. Now, the critical points that gave us function values of 0, those are something, but they're not the absolute extremes. So we're not really interested in them. Okay, another problem. F of xy is equal to xy e to the negative x squared minus y squared. That is going to be what we're optimizing. And the 2x minus y equals 0, this is our constraint because it's equal to a number. That's how we know. So the constraint is g of xy is equal to 2x minus y equals 0. Okay? And we're going to optimize f of xy. Okay, so first we want to set everything up. So we're going to set up the gradient of f is equal to lambda times the gradient of g. I'm going to need those first partials of f, and they're not trivial. They're a little bit more complicated this time, so I'm going to work those out kind of not in a vector. F sub x, it looks like I have a product rule because I have an xy and I have an e to the minus x squared minus y squared. So the derivative of x is 1. That'll give me y e to the minus x squared minus y squared plus xy, and then the derivative of e to the minus x squared minus y squared with respect to x gives me e to the minus x squared minus y squared times the chain rule, which gives me a negative 2x. And then this finally simplifies to be, it looks like I'm going to factor out an e to the minus x squared minus y squared and leave behind a y minus 2x squared y. Okay. F sub y is very similar. So I have a product rule because I have x, y, and then e with a y in it. So the derivative of y is 1. That leaves me x e to the negative x squared minus y squared plus xy times the derivative of our exponential with respect to y gives us our exponential to the negative x squared minus y squared times the chain rule, which gives us a negative 2y. Again, I'm factoring out the e to the negative x squared minus y squared and leaving behind an x minus 2xy squared. Okay, so those are the members of our gradient. Now I'm also going to calculate g sub x. Remember, g is our constraint, and it's 2x minus y, so g sub x is just 2, and g sub y is just negative 1. Okay, so I can go ahead and set up our Lagrange multiplier equation with the vectors. We have an e to the minus x squared minus y squared times y minus 2x squared y. And then we have an e to the minus x squared minus y squared times x minus 2xy squared. All of that is equal to lambda times the vector with components 2, negative 1. All right. Second, we're going to set up system of equations using the gradients and the constraints and then we're going to find our critical points. Okay, so the first equation that I get is e to the minus x squared minus y squared times y minus 2x squared y is equal to 2 lambda. The second equation says e to the minus x squared minus y squared times x minus 2xy squared is equal to negative lambda. Okay, and the third equation is my constraint, and it says 2x minus y is equal to 0. Okay, now this equation is not like, or this system of equations is not like the last problem. I have to find some different relationship. Like in the previous problem, I looked at the first equation and saw that I could factor it if I brought everything to one side. I'm not seeing that here. But I do notice that in equation 1, on the right side of the equal sign, I have 2 lambda. Equation 2, on the right side of the equal sign, I have minus lambda. So I'm thinking that maybe I could add these two equations together to eliminate the lambda. And the way to do that is I would take equation 1 and add it to 2 times equation 2. So I have to write that out though. All right, I do have the e to the minus x squared minus y squared in common with both of these. Equation 1 will just remain y minus 2x squared y, and then equal to 2 lambda. But equation 2, I'm going to multiply everything by a 2. So I'll leave the e to the minus x squared minus y squared on the outside and send a 2 through. So I get 2x minus 4xy squared is equal to minus 2 lambda. And now I'm going to add these. Okay? So when I add these, on the right-hand side, I have 2 lambda minus 2 lambda, so I get equals 0. On the left-hand side, I'm going to factor out an e to the minus x squared minus y squared, and then add the terms that are inside. So it's y minus 2x squared y plus 2x minus 4xy squared. And all of that is equal to my 0. Okay, so the cool thing is that I can see I've got a zero product property. This actually is factored. The exponential function is never equal to 0. So that means it must be the polynomial inside that is equal to 0. So I get y minus 2x squared y plus 2x minus 4xy squared is equal to 0. Okay, now this still doesn't look much better. It doesn't look like anything that I can work with. However, equation 3 has not been used yet. So notice in 3 that y is equal to 2x. So I could use that and substitute this into my problem equation. So we're going to sub this in here. Okay? So every y will get replaced by a 2x. That means the first y, that's going to be 2x minus 2x squared times 2x plus 2x minus 4x times 2x all squared is equal to 0. Now I just need to multiply everything out and combine like terms. I can see right away I have a 4x. Then I have minus 4x cubed. And then I have minus, that's all going to multiply. I have a 2 squared is 4 times another 4, that's 16. I have the x squared times another x, that's x cubed, equals 0. Multiplying that out, or combining like terms, I have 4x minus 20x cubed is equal to 0. I can factor out a 4x and leave behind a 1 minus 5x squared is equal to 0. And I get x is equal to 0, or I get x squared is equal to 1/5, which means x is plus or minus 1 over the square root of 5. Okay, just checking on my space here. I'm going to need to shrink down a little bit of my work so I have enough space to kind of finish up here. And it looks like that did not go over very well. Hang on. Okay. Sorry to take that time in the middle of a video. Okay, and then I can move this up here. Oops. Okay. This is starting to look pretty bad. Okay, let's get that y in there. All right, that gives me a little bit more space to be able to finish up this problem with. I'm hoping you have more paper than I do. Okay, all right, so what we have here are two cases. X equals 0 is case 1, and x is equal to plus or minus 1 over root 5, that'll be case 2. So it was a lot of work just to get to our cases, but we had to do it. So let's look at case 1 first, and that is with x equal to 0. All right. So if x is equal to 0, remember up above, we were working with y is equal to 2x. So then y will be equal to 2 times 0, which is 0. And so what we're getting here is a critical point of 0, 0. And our function evaluated at 0, 0 is going to be, let's see, it was xy, so that's 0 times e to the minus x squared minus y squared. So this overall gives us just 0. All right, may or may not be interesting. Let's look at case 2. So this is the case where x is equal to plus or minus 1 over root 5. And in that case, y will equal 2 times plus or minus 1 over root 5, which is plus or minus 2 over the square root of 5. Okay, so that means x and y have identical signs. They don't have opposite signs. So we have critical points of positive 1 over root 5 with positive 2 over root 5, and negative 1 over root 5 with negative 2 over root 5. And so we're going to need our function values at those points. F of 1 over root 5, honestly, we're going to get the same thing either way. Let's just see, okay? F of plus or minus 1 over root 5 with plus or minus 2 over root 5 is going to give us x times y. So whether or not it's positives or negatives, remember the signs are always the same. So when I multiply x times y and they both have the same sign, it's always going to give me a positive. And then e to the negative, and then x is squared. So it won't be 1 over root 5. It won't be positive or negative. It'll just be 1/5. And then y squared will give me plus 4/5. Okay, so this is going to simplify to be 2 over 5 times e to the minus 1. That's a positive number, and so this right here is going to be the absolute max because it's the biggest number, and then the 0, that is going to be my absolute min. And that's it. That's all we could get from this. We used all 3 equations. We got 3 critical points, and 2 of them gave us the same function value. And so there are 2 absolute maximum points, but there's only 1 absolute maximum value. The 2 points give you that same value. And then the 1 critical point that gave us 0, that's going to be our absolute minimum, and that only shows up in 1 place. Okay, so let's see. I'm going to stop it right here and pick up with another video just because of the timing with these Loom videos. But when we come back, I'll have, I think, 2 more examples to work out.